But that's something I can check on.
Okay, thank you.
UCLA has a question. I'm on Ranger. When I say module load IPM, says fail to load IPM.
Okay, if you do module avail IPM, do you see anything?
Let me see, just a second.
So on Ranger, you have to have the right, sometimes you have to have the right modules loaded.
Yes. One of the participants here is saying that for Eclipse exercise, we had to modify our .cssrc file yesterday. So she says she had to undo that.
Okay.
Let me try that real quick while your talk is going on.
Also on Ranger, one thing to be aware of is sometimes, so they have different packages configured for different compilers and different things. Sometimes you have to have the right compiler loaded in order to see the modules that are dependent upon that compiler. I don't think that's. I don't think that's the case.
We had to change from. We had to change from MVAPITch to OpenMPI yesterday for the Eclipse, so that might have caused it.
Right, but I kind of doubt that's what's going on with PD or with IPM. It's probably just something messed up in the environment. But you can send a note if that doesn't show up. I can check it out.
Sure.
Yeah. So any other questions? Okay. So this is just an example of the type of information you get back, and hopefully you can see this. I don't know why we need so many figures here, but if you have a very, very large number here, this would be megaflops, or this is in gigaflops per second. So there you get the overall floating point operations per second. Here's the percentage of the time that's spent in communication. And you can see the percentage of time in this pie chart here that was set and spent in all these different types of MPI calls. And there's different breakdowns of these things that you could get more exact numbers out of this, but it shows you that MPI broadcast is totally dominating here. Here, if you do have PAPI installed and available, then you could get the results of these counters through PAPI also. So this is just an example of, let's see. So again, this is sorted by task, so by MPI, so you can get breakdown across the MPI tasks where it's spending its time. So again, sometimes to alert you to a problem that's going on in your code, you may just need sort of an overall snapshot like this. And because the effort is so low to do it, then why not? And because the overhead is so low, also IPM you can run in just a production mode. You could just, if you wanted to look at in fact, this is what they did on one of the clusters. I think here at NCSA they just had all, I think well, maybe that was with PerfSuite. Another one we're going to get to. But you can load it and just have it run on all your production runs, and so then you can get really that's one way to eliminate the startup issue. If you have a lot of startup time, if you just run it on your production code, then for a full production run, it's not going to hurt your performance, and at the end you'll get a bunch of performance data out of your application. So you can also use this to sort of screen for applications that might be getting really bad floating point performance on a certain machine, and it could be a red flag to say, hey, we need to check out this application and see what's going on. Okay, so any other questions on IPM before we leave that? Okay, so we're going to quickly talk about PerfSuite, which is another tool that is similar sort of in design and in purpose to IPM. It's great for getting overall performance measurement of your code. It's easy. Again, you don't need to recompile. If everything's working properly, you don't need to recompile. Sometimes when when certain things change on machines with certain implementations, then the development might lag behind that change, and then you might have to go and resort to the the more difficult method of recompiling. That recently happened, which is why I bring it up. So if you run into a problem like that, then you just alert the developers to it, and they may or may not have already seen it. But if everything is working the way it should, then you don't need to recompile. A couple of nice things about PerfSuite is that it actually will give you a function level breakdown of what's going on in the routine. So IPM will give you the MPI information about the different MPI calls, but PerfSuite will also give you information about time spent in all the different functions in your code, the actual compute functions. It also works with OpenMP. One of the cons is that it's not as widely available as IPM on different architectures. It's basically you're limited to x86 and Itanium is what you can use PerfSuite for. And so I think its coverage on the TeraGrid sites is not quite as broad. I know it's installed on Popl at the PSC, and I know it's installed I'm pretty sure it's installed on clusters at NCSA, but we'll have to check again to know exactly where it is. But IPM is a little bit broader because it runs on more architectures. But PerfSuite has a couple of advantages of that function level information, and you can do it with OpenMP. So this is just, again, idea of how this works. You, again, are just setting some environment variables, basically. Source a file, which is going to set some environment variables. And then you just run your program with this ps_run command. And there's no need to recompile or anything. And then at the end, you'll have an XML file that was generated, and you run this ps_process command, and you'll get an output, which would look something like this, where you have, again, hardware counters that have been, that you may have chose to look at, and there's different ways to configure this, but hardware counters, and then it gives you some statistics, so it actually calculates some things based on those counters. So again, here you get the floating point operations per second, and you can get cache miss ratios, and it gives you a few of these things already pre-calculated. You could do all these by hand also. So just looking at the application that we're following here, unres, when you get, so we ran this with PerfSuite to look at the overall performance, and this was on an Itanium machine. And it gives you, when PerfSuite runs, it gives you output that describes, there's more than this, it's abbreviated here, but it describes the architecture you're running on, gives you some information about that. And then you can see how many floating point operations per cycle it did, and also the floating point operations per cycle. So the theoretical peak on an Itanium 2, it can do 4 floating point operations per cycle. And this is doing about 0.6 floating point operations per cycle. So it was getting about 15% of peak, which means it's not doing so great on Itanium. And it probably needs to have some optimization specific for Itanium, which is not surprising because it really wasn't written to run on Itanium, and Itanium's a little bit funny. So if you just run it on an x86 64 machine, so we ran it on the former Big Ben machine, which we retired at the PSC. And if we ran it there, then we got 33% of peak overall. So it was doing pretty darn good on that. And then this just can help you detect maybe some compiler optimizations are needed. And this one there's a bunch of tiny functions that need to be inlined, and so it's just issue that hint to the compiler and to the PGI compiler, and it improved performance quite a bit. So this is just a look at the parallel performance. You can see that it was doing okay up to about 16 cores, and then it rapidly would fall off for this particular size of problem that we're looking at here. So there's definitely some parallel performance issues here. So that's how you get the overall picture of your parallel performance, right? Just do a scaling study. So you just got to make sure on that again that you you're measuring that the time you're interested in, that you're not measuring the startup time. You either have to isolate that somehow, the loop time or whatever it is you need to get at, isolate the time of the time of interest, or run for a very long time so that you can mitigate the effects of startup and all that. Okay, so now we want to now we've looked at the overall performance of the code. Now we want to start to dig in. It's not performing as well as we'd like, and we want to find out why. So we're going to start to see what's eating up all the time. So in general, in most applications, there's just a handful of functions that are going to use up, take up 90% of your execution time. So that's nice, and that will help as we go down the line here. With the overhead. So again, I just mentioned that you want to make sure so that when you measure what's going on in those functions, that you're actually looking at the parts that you're interested in, the production part, the main loops, or whatever it is that's the most computationally intensive. And then when you look at the time spent in functions, if you're assessing the performance in parallel, then you absolutely need to look at the time in those functions at the high core counts. And generally, you just want to kind of take it up. So that's why you do the scaling study first. Measure the performance somewhere kind of midway up this scaling curve where it starts to taper off, and you'll start to see where those functions, what are the functions that are contributing to this problem in parallel. And you might want to take a couple points and see how the time in those functions changes as you go up in parallel. Okay, so I'm just going to show a quick example of how PerfSuite can give you that function breakdown. It's basically this is exactly what I showed you before, except you just give this PS run some different options that tell it that you want to look at cycles. There's different XML files which have different configurations. You can create these, and there's some defined by default. But you give it some specific options that tell you want to look at the time spent in all the functions, the number of cycles in all the functions, and run it with PS run, and then process the output. And you'll get something like this, where again we're doing sampling here, so it tells you how many samples when it was throughout the whole course of the run. It took 154,000 samples. It ended up in this function. So it sampled the state of the program, and at various intervals, which I guess, so yeah, you could probably figure out how often it's sampling, but it's certainly not every time. But every time it stopped the program and looked at it, 154,000 times it ended up here, which ended up being about 77% of the total time. So the self time here, this would be the exclusive time, right? This is the time actually in that function. And then the total time would be the inclusive time, so the time spent within that function or within any function that was called by that function. So you can see for this one, this is the real computational workhorse function. All the time spent in that function is actually exclusive time. Whereas this one probably called this function here, because 84% of the total time is spent in this function or one of its child functions, but only 7% of the time was actually spent in that function itself. It can also give you a line summary, so it can show you where in your code, where in your code, the lines that were responsible for, the most significant amount of time. So where in this file here it was the time taken up. So you can go back to your source code and look at that.